Okay, now we're going to talk about our first actual species distribution modeling algorithm, which is Bioclim. And this one is often introduced first for the simple reason that it's quite easy to explain. It helps get a lot of the kind of concepts out there um, without actually getting too much into the hairy details of how a model is really built. So what we do with Bioclim is we basically take the occurrence points of our species in geographic space. We extract the set of conditions under which those points occur, and we can sort of map them into the space of some environmental variables, as I sort of showed you before with the simulated data. So this is Bio 1. This is one Bioclim predictor. This is Bio 2, another Bioclim predictor. And this is the values for the points where our species occurs in that environment space. So, this is a place where our species occurs, and it has a value for Bio 1 of, I don't know, about 110, and a value for Bio 2 of about 83-ish, right? So, yeah, this is just the distribution of our points in environment space. Bioclim models basically just say, you know what, our species probably mostly lives under the conditions it likes the best. So the places we see it the most often are probably some of the best quality habitat. And that's a pretty common assumption in species distribution modeling. It might not always be true, but we usually start from the assumption that something like that is true. So what Bioclim does is it basically takes the marginal distribution of our species with respect to a specific environmental gradient. So here we've got basically these points turned into a histogram. So this dot is this, and I got a little bin here, and that's these points here, right? And so we've got more, higher bars here under the conditions where our species is most common. And then we can do that for the other variable as well. And so we have these two marginal distributions of our species with respect to these environmental gradients. Okay, and then all the Bioclim does, it sort of starts in the middle there and says, okay, we're going to say this is the center of the species niche, and places close to that, or environmental conditions close to that, are probably the highest quality habitat for our species. And so we'll take essentially this central 10% of our species distribution with respect to this environmental gradient and say that's its favorite set of conditions for that specific environmental gradient. And then things that are slightly farther out, we assume it likes slightly less. And things that are much further out, we assume it likes considerably less. And then what we would do is we would take the other environmental gradient, Bio 2 here, and we'd essentially do the same thing. We'd start at the middle of that distribution, say that's the best quality habitat, then we've got the somewhat less good habitat, and then we've got the not very good habitat farther away from the center of that species distribution, right? And we do that for the two axes independently, and what that turns into in this two-dimensional space is basically a kind of histogram, a two-dimensional histogram that says, okay, these really common sets of environments where we see our species most, the most central points in our species environmental distribution are the highest quality habitat, and then further out is lower quality, and further out is lower quality, et cetera, et cetera, et cetera, right? So that's a very kind of straightforward way of doing things. Essentially, we've kind of created two independent histograms of habitat quality that are simply based on percentile rank of the environmental observations in the overall distribution of those environmental observations. And you can see this is a very kind of simple shape and environment space. So a Bioclim model is always going to be some sort of box or cube or hypercube or whatever. And that's kind of straightforward and easy to think about. It doesn't make a ton of assumptions about the sort of functional response of your species to a set of environmental gradient. It's just ranking points by where they fall in the marginal distributions of those environments. So yeah, it's straightforward. It's going to have, these models don't extrapolate essentially very much past the environmental conditions they're trained in. In a sort of unidimensional sense, they don't extrapolate at all. In a sort of a two-dimensional sense, you could see it's saying there's some habitat that's good over here that falls into combinations of environments that don't exist in our data. And that's just because it's sort of treating these two things as independent. So it can sort of extrapolate a little bit in a multidimensional context, but not really in a unidimensional context. So it's not going to push past the maxima or minima of our data in either of these axes, but there may be combinations that it kind of extrapolates into. I hope that's clear. And it's because it's sort of based on percentiles, and typically we just take the sort of central 90% of a species distribution as, the sort of edge of the climate envelope. It's tempting to think that these models have a fixed omission rate, that they will include 90% of your data. That's actually not entirely true. Right, so along any individual axis, viewing that axis on its own, right? So now we're going to do this x-axis here. Viewing that axis on its own, this model is going to include, within this 90th percentile distribution, 90% of your points. And that means 10% will fall outside, right? But then, when you add in Bio2, it's going to include 90% of the points here along that distribution, but then it's going to exclude 10% along its axis, right? So along this vertical axis, it's going to exclude these and these here. Why do I say that doesn't actually place, well, it doesn't place a fixed ceiling on emission rates? So along a single axis, the emission rate is fixed. But in terms of the whole model, there can be stuff that falls out of the boundaries for the x-axis, and therefore is deemed unsuitable, that does not fall out of the boundaries for the y-axis. So it falls inside of the distribution here, but outside of the distribution here. And what that means is that the actual omission rate, like something is actually falling outside of the niche model if it's outside in any single dimension, which means as you add more dimensions, you add more ways for points to fall outside of the model. So there is a ceiling placed on emission rates, but it's not a fixed ceiling for for all numbers and dimensions. A lower dimensional model will have a lower maximum emission rate than a higher dimensional model. So by the time you go up to putting 19 Bioclim variables into a Bioclim model, you could actually have a really, really high omission rate because a lot of those points are going to fall outside of the central 90% on one of those 19 axes, and they only have to fall outside on one of them to essentially be omitted from the model. So, low-dimensional Bioclim models tend to have low omission rates. As you add dimensions, they tend to have much higher omission rates. So that's worth keeping in mind. And yeah, other than that, I know people kind of like to, talk smack about Bioclim models because they are so simple. The method is almost 40 years old now, I think. Yeah, anyway, it's a quite old method. It's quite simple. It's very straightforward. It's not exciting. But the thing is, it often works okay, and it makes a lot fewer assumptions than a lot of the other methods do. That said, it does not extrapolate outside of the sort of current environment space much at all. And so if you are trying to make a model in one time and space that you can predict to another time and space, Bioclim models are probably going to predict that a lot of that new climate space that's newly available is unsuitable because it wasn't there in the training region. And so they do not typically extrapolate a whole lot. And that's something to keep in mind when you're actually building these models. They don't extrapolate, and as such are somewhat unlikely to do a particularly good job when transferred.